So let's take a look at the idea of volumes and double integrals. Now, in a similar way that we define the idea of an integral back in Calc 1, we can think about the functions of two variables defined in a closed rectangle. And Calc 1 is on a closed interval. Now we're going to think about it in terms of a closed rectangle. So I'm going to define this closed rectangle R as being AB by CD. Now this is like x coordinates, y coordinates. So on x from A to B and y from C to D. So it's this by this. This x is not like a cross product. It's like a 3 by 5 rectangle or something like that. So this rectangle is going to be equal to all the points x, y that are in R2 such that A is less than or equal to x, which is less than or equal to B, and C is less than or equal to y, which is less than or equal to D. So I'm going to have this closed rectangle on the xy plane is what I'm really talking about here. So let's start with the very simplified scenario initially where f of xy is strictly greater than or equal to 0. So the graph of f is in a surface in 3 space. So in other words, we're saying that z is equal to f of x, y. So what is this going to look like? So if I have some surface here, let's see if I can do a halfway decent job of trying to draw this. So this is some surface. And I'm going to think in terms of what it's going to look like when I project down to the xy axes. That's not too bad. And of course, I'm going to need some axes on here. So see, this is going to be my z-axis. And let's say that my y-axis runs like this. And my x-axis is then going to run, I should get rid of this negative z, make it a little bit easier. See, my x-axis is going to run kind of like this. Okay, now what I've actually described here is I've got x equal to a equal to b. So here's a range of x that gives me this piece of the rectangle. And then I've got y over here from C to D. And this is actually describing this rectangle that I'm working with. Yeah, I kind of tilted this a bit, but I think you get the general idea. This should be more parallel so you can better see what's going on. This surface up here is actually what I'm thinking of as z equals f of xy. So what I have is the surface is actually equal to all the points x, y, z that are in R3 such that 0 is less than or equal to z, which is less than or equal to f of x, y, and x, y are in this region R. Now I'm referring to this rectangle down here, R, as this region I'm talking about. This right here is what I'm thinking of as R. That's that guy. So if I'm thinking of this as my surface S, then what I'm really talking about here is trying to find the volume between S and the xy plane. So the first thing I'm going to do is I'm just going to look down onto the xy plane and concentrate for a moment just on that rectangle, that region down there on the xy plane. So when I do that, what I have, scoot that a little bit farther, what I can think about is simply my xy axis, and I have this rectangle sitting here somewhere. Of course, I'm going from A to B, C, to D. That's defining where my rectangle is. And I'm going to take this rectangle and I'm going to break it up into a bunch of smaller rectangles. So I'm just going to do a couple of them here. That's good enough. So as an example, this guy right here, I'm going to call this rectangle Rij because it's in row I, column J. That rectangle has an area associated with it. Now in here, I'm going to pick a point anywhere in there, and this point is going to end up having the coordinates xij, yij, and put this asterisk on it, denoting that what I've got here is any point inside that region. So now the area of Rij, that's this particular rectangle here, is actually equal to, I'm going to call it delta A, which is the base of the column reaching up from the XY plane to that surface S. Therefore, the volume of the column, any individual column, is then going to be f of xij yij times delta A. Therefore, I can say that the total volume is going to be approximately equal to the sum I equals 1 to, say, m, then the sum j equals 1 to n of f of xij yij times delta A. So what this is simply a double sum, so I could add up all the areas by rows and columns. So clearly this tells us, from what we understand from back in Calc 1, that the actual volume is going to be equal to the limit, as m and n both go to infinity, of this double sum. I'm just going to say the sum over I, the sum over j of f of xij yij times delta A. So this will then lead us to the definition of a double integral. The double integral over the rectangular region R is simply the double integral over R of the function, the surface, f of xy, dA. So I'm taking the derivative with respect to the area, which is equal to the limit, as what I just got done writing, m n goes to infinity of the sum I equals 1 to m, j equals 1 to n of f of xij yij delta A. Of course, if the limit exists. Now this double sum is actually simply referred to as a double Riemann sum.